Hello everyone. Welcome back to the new session of the Reinforcement Learning Reading Club. We had a kind of long break during the summer, and now we are back with more talks, and we have already scheduled, I guess, three more, one of which will be presented today. And please let me know if you're interested in presenting the paper. So the basic idea is that usually the presenter picks one of their favorite papers. Usually it's not their own paper, it's just something that, for example, from some high profile venue or something like that that they have found useful reading. And then we have a short presentation for about 20 minutes, after which it is followed by an informal discussion. And the whole session usually takes about 40 minutes to 1 hour. So today we have Nikita Kostin, a doctoral student at Aalto Robot Learning Lab, and he's going to present a paper from ICLR this year. So Nikita, you may begin.
Thank you very much for the introduction. Hello, everyone. I would like to present a very interesting paper, state-of-the-art paper in safe reinforcement learning called Constraint Policy Optimization via Bayesian world models. So the outline of my talk is, I will present first introduce the main concepts that we will need in order to describe the method. Then I will talk about previous state-of-the-art, or at least the algorithm that introduced safe reinforcement learning as it was used in the paper I discussed. And then I will also talk about model-based reinforcement learning, since the constraint policy optimization via Bayesian world models, which I will call Lambda. This is the name given by the authors. They make use of model-based reinforcement learning a lot. Then I will describe the Lambda algorithm itself and present the experimental results. So the introduction, first, just a brief, some words about why we would care about safety. This is very important thing when we're talking about autonomous driving, let's say, or robotic manipulation in very fragile environments with modern robots, which are quite expensive, and they need to be safe in order to be applied in the real world and to work along with humans. So safe control is very important, and it's been a long-standing question in control theory since its starting point. And only now we are getting closer to apply this algorithm to the real world. Okay, let's start as usual in presentation for reinforcement learning with definition of Markov decision process, since it's the main block of the reinforcement learning itself. So in MDP, we have the set of states, set of actions, transition probabilities, which basically declares how our state will change according to actions that we apply. Also the reward function, which shows how useful was some particular action or being in some particular states, and the initial state distribution, which basically gives the probability distribution over initial states that agent will start from. And in order to introduce safety, we will use the set of constraints that will also be provided by the environment. And so we need to extend MDP to be constrained MDP, CMDP. The additional ingredient here is, there are two of them. So the set of constraints, which will be also given by the environment once the step was taken, and also the constraint limits, which will show how much constraint violations are allowed in the environment. This basically should be set by humans or some other oracles, so it's not be set by the agent itself. And yeah, also let's recap some of the main quantities that we will use. So in reinforcement learning, what we usually talk about trajectories. So trajectory is a sequence of state and actions. And also, like we may think also that trajectory would include rewards and costs. But mainly, if we, let's say, will learn in the future, we will learn the reward and the cost model. Therefore, we could just store states and actions. There's some useful functions that we will need. There are value function, which is basically, it shows how useful it is to be in state S given the policy, for following the policy from that state. And Q function is, it shows how useful it is to take an action A in state S and then follow the policy. And that one advantage function is basically different, so it's averaged over actions. So it shows how on average some action is better than the average return from that state. And the objective in reinforcement learning to be maximized is just a sum of the reward, discount the sum of reward, and with the expectation. So we want an expectation to increase our performance. For the constrained reinforcement learning, we will also introduce similar things. It's basically, we will just swap the reward with the cost that we received from the environment. And we will make use of these quantities later. And importantly, the cost in the bottom line, we of course, we don't want it to be maximized. We want it to be minimized, or at least bounded. So this is the main difference, because people usually do not understand the difference between costs and rewards. So one thing should be maximized as much as possible, while the other should be bounded. So we don't want, of course, it would be great to avoid costs, like basically collisions at all. But the main thing is to bound the sum of the costs. It's the main difference. And the goal of constrained reinforcement learning is to find a policy that will basically gives the maximum to the objective function, the task objective function, so the JP without the subscripts, while being the feasible policy. What does it mean? It means that it should be inside the feasible set, the set of policies that obey the constraint on the costs objective. Yeah, so this is again, so the constraint problem that we will solve is that we will use this constraint as a subject to constraint, and we will search for the policy to obey this constraint. Okay, how? Yeah, so the main work in that area is constraint policy optimization. So, yes.
Is it okay if we ask questions?
Yes, sure.
Yeah, so can you give some example of this like constraint MDP? So basically we have reward, but on top of that we also have some constraints, which is a different function, I believe, right?
Yes. One of the simplest examples that we will use later in the experiments is that we basically receive C. So basically, usually C is a binary number. Every time we are receiving it from the environment is either 0 or 1. And so the basic example is that we will receive 1 once we collide it with the obstacle and 0 otherwise. And therefore, the obstacles are located somewhere in the environment. And basically the environment will tell us once we collided with the obstacle, since we have the simulator and we could detect the collisions. In the real world, it's a bit tricky right now, and yeah, we're working on that. But in simulator, it could be easily set up.
Okay,
So I have another question. So this with this kind of like so the JCI. So this is a kind of like a cumulative sum of these costs.
Yeah.
Or is this kind of like an expectation of the cumulative sum of costs?
Yeah, it's an expectation.
So now if we at one time step we get for, let's say we at time step 2 we have so let's say we have two different policies. So for the first policy we get at time step 2 we get or cost of 1 in expectation. So we always collide in time step 2 with policy 1. And then we have a policy, another policy for which we get a 50% chance of colliding at time step 2 and a 50% chance of colliding at time step 3. Then we get the same J, but in the other case, so in the first case we collide always, and the other case we sometimes collide. So does this make sense, this kind of like cost formulation?
Yeah, it makes sense as long as this number of collisions in expectation is bounded by the number that was given by the humans. So if for humans it's okay to be collided like the times that they said, that is okay, and it's feasible policy, and we will basically use it and try to improve it. Otherwise, these policies will be discarded, and basically the gradients for new policy search will be given.
I didn't quite understand. So my question was about, so if you have a policy that always collides and a policy that sometimes collides, but they both get the same J. So this was the question.
But like in expectation, the second policy would provide a lower JC.
Why? So if you have like if you have at one time step you get 0.5 and another one 0.5, together they are 1 with a discount of 1.
Yeah, I forgot to denote here gamma to the power of t. Sorry.
Yeah.
Summary.
Yeah, but the point is that so you have one policy where you always collide for sure 100% of the time at a specific time step, and you have another policy where you collide with 50% chance at one time step, and then you collide with 50% chance at another time step. But with both, you can get the same J.
No, if you will include gamma, then
okay, fine. So let's say you collide with 0.5 divided by gamma to the power of t with the other one, then you get always the same same. So wait, I will write it here like so if you have like so I have like one policy, let's say this is like policy 1, and then you have here like policy 2, and then at time step 2 you always get like the CT1, and let's say with policy 2 you have a time step 0, you have the you get like CT is CT is 0.5. I don't know if this is very nice, but then that T is 1, you get CT is 0.5 divided by gamma. So for both like GA pi 1 and so these are then the same, right? But for this policy here, you always collide for sure. You are 100% sure you always collide. For the other one, you just sometimes collide. So this
Yes.
seems to be like a fundamental property of this cost formulation.
It seems so, but I guess, like, again, so we're not pushing the so later we will see in Lagrangian approach that once the constraint is satisfied, so once this cost sum is bounded, there is no gradients for changing the policy to be more safe. So if this both of these sums will provide such a number that is not under the boundary, then the policy will be changed anyway. So none of these is acceptable. But if the policy is bounded, the sum of costs is bounded, no gradients will be provided to make policy more safe. And both of these options is acceptable.
Well, I mean, it depends what you want to optimize, I guess.
Yeah. Of course, we want to optimize the task objective. We want to maximize the sum of rewards, but we want to keep this sum of costs just bounded. We don't want to minimize it as much as possible. And
okay.
once we satisfy the boundary condition, we won't get any gradients. We will see the objective later that will show.
Yeah, okay. So of course, I guess it also provides like an upper bound. So if you say that you had this, I think you had something like this. So and if you say that the D is 0.1, then you know that that the highest probability at any time step is 0.1. So because this kind of gives you an upper bound also on single time steps.
Didn't understand that, but
yeah. So if you because from like if you think about the practical perspective, so typically what you want from safety is that you can say that okay, we will never collide with the probability of or with for 90%, like there's a 90% chance that we will never collide when we execute a trajectory, and even if you sum the costs together, then you get an upper bound on this, like by just setting D to something like this, for example.
Yeah,
but it kind of like but from the optimization point of view, it kind of like the kind of like what kind of solutions this kind of formulation prefers. It's yeah, I don't know. Does this make any sense actually? So
at least it makes sense in the experiments where the number of collisions is like under the boundary. But the question is how to set this boundary. Yeah, it's definitely an interesting question. And yeah, for example, one paper did implement the curriculum learning for this D. First start at very high number and lower it as the agent progresses its learning. And yeah, so it's flexible number that may change from time to time actually. But in the experiments later, it's fixed since as a design of the environment.
Okay, yeah. So is there an assumption that the task always terminates when there's a collision?
No, it's
there's no assumption like that. Okay.
No.
Okay, that would also change things a little bit. Okay. Okay, yeah, but thanks. This is very interesting. So
Yeah, thank you for the question. Okay, so let's move to the CPO. So let's also recap some of the policy optimization algorithms. So in policy gradient, we want to maximize the sum of advantage functions in expectation, which basically provides lower estimate than maximize the sum of rewards, but it's still unclear how big of a step we should do, how big the learning rate should be in that objective. And in TRPO paper, authors added additional constraint to that formulation by just limiting the update size in policy, in terms of parameters, by just constraining Kyle divergence between old policy and a new policy. And kind of a similar idea, so it's just an idea of trust regions, was used in constraint policy optimization. So the main theoretical idea that we will just use, and for those who are interested, I refer to CPO paper. The main theoretical result is that they derived a bound for cost objectives, and using that, they won't just, so it's a upper bound for the next policy parameters, and they basically just extend number of constraints in TRPO setup with additional constraint, where the constraint, they basically bound the constraint the upper bound on the next cost, some of the cost for the next policy, and one seek to find the policy such that it's satisfy this constraint. So yeah, and inspired by TRPO paper, they proposed to use approximations of the objective and constraints, and they made a first order approximations to objective and the cost constraint, and second order approximation to Kyle divergence, and therefore they will just solve this problem iteratively using Lagrangian multipliers method, and arrive to the quite good results. But main problem of this approach is, first, it's on policy, so as TRPO is, and the second is so it's getting rid of a lot of data, and therefore it's quite sample inefficient. And second, this approximation is sometimes inaccurate, so the results in terms of safety and in terms of task objective is quite bad, as the paper I'm talking about will show. Yeah, model-based reinforcement learning. Let's recap some of the things that we will need. So in model-based reinforcement learning, we are trying to learn the dynamics, the probability function over the next state given current state, current action. And one way we could use this learned model is just to create an ensemble of these learned models and just use it for planning without any interactions with the real environment, as it was done in probabilistic ensemble trajectory sampling. And the other thing is like Dyna style algorithms, where we just use learned model to generate the trajectories and just do our similar on-policy algorithms, but since they are done using synthetic trajectories, it's not that sample inefficient. So it's actually quite sample efficient. Yeah, and one of the main architectures for learning model, when we're talking about partial observability, this is especially true for Lambda paper, because they use images as observations and they need to infer latent states, is recurrent state space models. So here we need to extend our MDP or CMDP with the observations, with an additional notion where the observation is sampled from the probability distribution condition on latent state, and in case of RSSM on the latent state, deterministic state. And so deterministic latent state is computed using hidden state is computed using recurrent neural network. And so the main thing that RSSM provides is the encoder that basically provides a filtering distribution over next state given observations and actions as a factorized distribution. And in order to train RSSM, authors of Planet, where it was proposed, build a lower bound on the marginal likelihood, and they just proposed to maximize it. And after some math, we could arrive to the lower bound that we will maximize, where parameters theta and phi, parameters theta correspond to two models. It's observation model and latent dynamics, and also the recurrent neural network from the previous slide. And parameters phi correspond to our encoder that we learn. We will use it later in Lambda algorithm, but it's just a recap so that people understand the whole picture. And an additional tool that Lambda paper made use of is the stochastic weight averaging Bayesian or SWAG. So the main motivation to just use it is that in order to make predictions, model should be sure about how large errors it has in certain states. So if model mistakes a lot in some particular state, it should provide an information for the agent to also not rely on model predictions a lot. And one of the methods to do this is to use ensembles, as I mentioned before. And for models like RSSM, which is quite parameter-rich model, it's very expensive in terms of memory and compute resources. And an alternative approach is to use SWAG, which is basically algorithm to infer approximate posterior over the weights of dynamics model, given the data it saw. And by sampling from this posterior, we could do Bayesian model averaging or posterior sampling, as it was done in Lambda. So the SWAG algorithm works as the following. We will use SGD updates to train our model. And we could use either constant learning rate schedule, or cosine annealing, or cyclic with some cycle factor. It basically doesn't matter so much. And every C SGD updates, we will just use the current weights to update 3 quantities, to update the running average over the weights, and 2 other things: second moment, which is shown here, and also the low rank deviation matrix that basically will store k latest columns, k latest measures of the difference between the current theta and the running average at that moment. And it turns out that after doing this, at first glance, it's quite weird procedure. It turns out that after some iterations of SGD, we could get the posterior distribution, Gaussian posterior distribution over the weights, and it has a not only the better estimate than the current theta, so the experiments showed that, but it also provides a estimate of the uncertainty in terms of weights. And this is quite impressive, because now we could sample from this distribution and do all the things as we would have a true posterior over weights. And it was done to the cost of storing basically a couple of more copies of our weights. And they shouldn't be stored on GPU. It's an advantage. So we shouldn't store it like ensembles where we need to backpropagate gradients. They are very computationally inefficient. Here we shouldn't do any copying of the network and doing the backpropagation. We just need to store it on CPU, let's say. And as a result, we will still get the distribution, posterior distribution over weights. And yeah, so how all these ingredients that I've talked about were combined to build a lambda algorithm. Let's return back to the objective in constraint policy optimization. So we want to maximize the sum of rewards that is shown here, subject to some constraints, sum of costs. There could be many of them, not just one. There could be many constraints. And an alternative approach to that problem is not to make the approximations that CPO did, but apply Lagrangian multipliers straight away to that problem. And so the objective that was proposed in lambda is to just use the constraints in terms of just a difference between the sum of costs and our limits, and also use additional term which will correspond to the change between feasibility and infeasibility sets. It will make this, it will add smoothness to the objective, to the just a pure objective. And after doing some math, we could find that optimal Lagrange multipliers and substitute them back to that objective, we will arrive to the following objective that we want to maximize. And as one can see from here, once we do not violate the constraints, it will be set later. But so this objective, this whole sum is equal to 0 once JC of pi is below D. So once this thing is negative, I just didn't have enough place to do the math, but I will show later that we define the objective in a way that once we obey these constraints, this term equals to 0, and therefore no gradients are provided in terms of the safety. So we only care about the maximizing sum of rewards once we obey the constraint. That's in other words. Yes, and in order to maximize the objective on the previous page, we will introduce the critics in our formulation, and the task critic and the safety critics are trained using the temporal difference error in the following way. So we will just use our learned model to sample the trajectories, synthetic trajectories, and we want to just minimize the mean squared error between our current estimate and the V lambda, which is defined as the exponential weighted average over the in order to provide a good estimate for the target in terms of bias and variance, we would like to not just to make the target as a sum of rewards, but combine the n-step return with the exponential weighted average. We will just form the following estimate. And the same loss functions can be used for learning the critics, safety critics. So just replace all the psi's with psi-i's, and yeah, that will be, and the r's with the c's. And another interesting novelty of Lambda paper is that, and is that how they use the SWAG procedure that I described before, in order to make the most pessimistic estimates of the value function for costs and the most optimistic estimates for the values of task objective. They use the following upper confidence bound estimation, where they just do the several samples from the posterior over the weights, and they just evaluate those weights with the, so basically they sum the trajectories from the corresponding models and evaluate the V lambda, and afterwards they take the maximum over those estimates. Usually n, in the Lambda paper, the authors used n equal to 5, and the similar numbers are set in SWAG paper. And the intuition here is that if we would take the maximum estimate over the value function for the rewards, it will provide an optimism in terms of we will hope, and we will take say agent that our highest estimate, because it will provide an optimism in the face of uncertainty. At the same time, the maximum over value function for the costs will provide the basically the worst possible estimate, and therefore it plays the role of like pessimism, and makes agent fix the policy so that it still obeys the constraints. The policy optimization in Lambda algorithm is done using the just a approximation to the objective. Again, using the sampled synthetic trajectories, and the policy is modeled as a Gaussian distribution as usual. And yeah, here, so let's again denote the this part, the last part in this objective. We will just denote it as a capital Psi, and so as I mentioned before, we will consider it to be just we will consider it to be just a constant if the constraints are satisfied, and we will consider the difference between, so basically the degree of constraint violation, two terms, two powers, and this will provide a large gradients if the constraint is not satisfied, and no gradients are provided if constraints are satisfied. And yes, and so the final objective that we will use for the policy, it looks like this. So we want to maximize the task objective with respect to the policy parameters, with some additional constraints that are just in the form of additional terms. And so as a result, the following objective was used in Lambda paper, which is that we want to minimize this objective, therefore we will maximize the value estimate for the rewards, and also we want to minimize some of our constraints. So we want the constraint to be satisfied, and again these states are sampled from the learned dynamics, so this synthetic data, and as our model learning progresses, we could basically use only synthetic data without any interactions with the environment, and therefore we are getting we are getting much sample efficient. And what authors mentioned, and I don't understand to the full degree, is that they can also do the backpropagation through the model. And this is quite interesting, because since we saw the equations, we saw the loss functions for learning the parameters theta, and we even saw the SVAC procedure, but nevertheless, they are using the gradients from the policy optimization objective to update the parameters theta, and or at least they may use these gradients just not doing the updates on theta, but provide these gradients later on. So this is a bit unclear to me right now, how this it was used, but already the paper introduced quite complicated architecture, so I don't think it's so important right now. Yes, so the full algorithm finally. As I mentioned before, we will learn our model using the real data from the environment. So we will collect this data using random policy or offline data set, for example. And we will learn theta and phi as I showed previously. And after that, we will use the variational encoder provided by RSSM to infer the next states. And then we will do the estimates of the value function and cost value function using the algorithm that I showed before, the upper confidence bound estimate. And then we will update the value functions and the cost value functions using the Bellman, using the mean square error, update the psi parameters using our policy optimization objective, and update lambdas. I haven't shown these equations, but they are very simple. And basically that's it. We will do this procedure, collect more data, and repeat. And the results are quite impressive. First, I will introduce the safety gym, the main playground for constraint optimization algorithms. This refers to the question of the example of safe reinforcement learning environments. So here, these blue circles represent the no-go zones. So once the agent and this red car, once it touches or goes inside these blue circles, it will receive the constraint violation flag that will provide it as 1, and therefore the agent understands that this is he or she shouldn't go there. And the task is basically to push the bricks to the yellow dots while avoiding the blue zones. And so, as I mentioned before, the agent sees the observation as images of the environment, and this is how they look like. And they are 64 by 64 size, and the agent use the RSM to deal with them. And the main comparison here, for the comparison, authors used 4 algorithms, the CPO that we described. TRPO Lagrangian and PPO Lagrangian are the algorithm that basically the additional thing to their objective is the difference between the task cost and the boundary, the DI, with some Lagrange multipliers. So almost the same thing as it was done in Lambda paper. And CEM-MPC, yeah, it's a algorithm that it is basically probabilistic ensemble trajectory sampling with also learning the cost model. And when using the MPC in the evaluation phase, this MPC not only maximizes choose the trajectories with the maximum reward, but also those trajectories which obey the constraints. And yeah, so as we can see from this plot, yeah, so Lambda algorithm provides the much better task objective, while being very good in terms of the number of constraint violations. Yeah, so very interesting plot that authors provided is that they can measure the task objective safety at the end of the training and safety during the training as normalized with respect to the performance of PPO, pure PPO without the Lagrangian. And it turns out that Lambda has the maximum of task objective and safety training, while being very good in terms of the safety during training. Not the perfect one, but if we will compare on the both three metrics, it's the best. And yeah, finally, during the ablation studies, Lambda authors provided several experiments, and two of them are very interesting. First experiment is when we will just get rid of the upper confidence bound estimate for the value functions. And so the yellow one is the one that uses the posterior distribution over the weights just to do the Bayesian model averaging. And Lambda, the green line shows the procedure that we described. And it turns out that it's, of course, that there is not a big gap, but there is a quite good understanding that it's this procedure of upper confidence bound for value functions indeed work. And so the other experiment is that the authors suggested to get rid of the safety term in a policy objective, this one. So just to get rid of these terms and just optimize policy to maximize the sum of rewards. And the experiment showed that the unsafe Lambda is even better in terms of the average return, but it's completely unsafe, of course. And it basically showed how important it is to account for the constraints. Yes, this is all for me. If you have any questions, I would be happy to answer them. Thank you.
Yeah, thank you very much, Nikita. I guess we have about 5 minutes for questions and answers. So, yeah.
I will chip in. First of all, great talk. That was really good. I heard there's lots of things in the paper which they you kind of need to go off and read, and you covered all that really well, like swag and stuff. I guess for me, like more some interesting comments on the paper. Yeah, interesting to get thoughts. So often like when we use like Bayesian world models, we use ensembles, and like Bayesian neural networks aren't used that much. And people always used to hypothesize this was due to their inability to capture multimodal posteriors. But in here, it looks like they've got a Gaussian posterior over the Bayesian neural network weights. So I think that's a really interesting result in itself. And then the other thing that I was talking about was the constraint satisfaction. So like using like the expected constraint satisfaction just seems like a very weak notion of safety, right? So like in risk analysis, like what if there's super high variance, right? So actually certain samples you do violate this. So a stronger notion is to use like the expected value and the variance of the constraints to make sure that they're both bounded. And then an even better notion would to have some probabilistic constraint instead of the expected value. So yeah, I thought that was interesting, just because they have these expected constraints, and then they're kind of, you're sampling a dynamics model, you're trying to find the dynamics model like in this pessimistic way, right?
But pessimistic for the costs and the optimistic for the task objective. Yeah,
exactly. Yeah, I thought really good paper, really good presentation. But yeah, I thought those, maybe we're going to meet on Monday. Maybe it'd be interesting to chat about those points.
Yeah, looking forward to. Yes, I also wanted to briefly mention that this the not this plot. Yeah, this it's very good to mention that it's the Lambda paper indeed cares only about the average number of constraint violations, and in some way it is a drawback, because the variance could be very high. But again, during this upper confidence bound estimation, we will choose the worst. So it's kind of avoids this problem. Of course, not totally, but it kind of helps. It's of course it's much better than in CPO paper, at least. Yes, but I of course, I was thinking of not the average number of constraint violations, but maybe accounting for the worst case would be also interesting. So try to estimate not the average, but the maximum, over basically estimate the maximum of some value given the data, not the average. But again, if we're talking about the simulation, then maybe it's not that it would be very important for me. It's very interesting how to do this data collection at first, because in the beginning we don't have any understanding where the objects are located, and we could create a lot of collisions. Yeah.
I mean, like in robotics, it can be common to often you can have your agent and then you can collect a data set locally around the starting state, and you can kind of do that safely, before it goes out into the wild. So you kind of have this initial region and you can collect the data set easily and just pull it back. And then from there, you let it sort of expand its safe region by exploring. And I had one other thing as well. You mentioned about the taking the gradient through the model to optimize theta. I mean, unless I've misunderstood, but I think they were just optimizing the policy, and the point was that if when you have a Bayesian model and you're sampling from it, they probably had to use the reparameterization trick and certain things to be able to get these gradients. But I think they're just optimizing the policy, right?
Yes.
Yeah. So
and since it's a sequence, we could backpropagate gradients through the dynamics model, not updating theta, but use these gradients to then later to backpropagate again to psi.
Exactly. Psi. And that's kind of if you forget, it's kind of, I feel like that's just pretty normal, right? That's what's done in Pilco, other algorithms. Yeah, but again, I don't understand. I mean, the RSSM is quite complicated structure. It's quite complicated architecture. It's not that easy how the gradients would flow there. So it's those provide a scheme how they use this backpropagation, but I maybe it would be better to have the implementation of these. Just to through it. I guess in Planet, they use the gradients as well, right?
Yeah.
So the novelty of this work is just they essentially extend the state space model to be Bayesian, right? Did Planet do that? I can't remember.
No, they don't do that. But Planet also doesn't have any policy, so they use just CEM. Yeah. So Dreamer does have a policy. That does have a policy, yeah. And so basically the novelty is just to adding the Bayesian nature to the model. Yeah.
Okay. Yeah, my inclination then would be like the reason they've commented on it is just because sampling the posterior over the weights, to sample one of these dynamics models, like if you have to do that, but they're not even. Yeah, I don't know. I have to think about it.
Yeah.
Okay, I guess we can wrap up the meeting then. So thank you again, Nikita, for the interesting presentation, and thanks everyone for attending this session. And hopefully we will meet again in 2 weeks. Have a nice day.
Thank you. Bye.
See you, everyone.